So, radioactivity is the release of a high energy particle or a high energy electromagnetic radiation from the nucleus of an atom. And atoms can eject particles or energy from their nucleus. We're going to take a look at that when we start looking at the different types of radiation. And when they do this, this is what we call a radioactive particle. So a radioactive nuclei is going to spontaneously decompose into a smaller nuclei. So you start off with a larger nucleus and it'll get a little bit smaller as a result of casting off a high energy particle or possibly even some energy. And this is what we would call radioactive decay. Now, the reason why they do this is because they're unstable, and Mother Nature is always seeking a lower energy state, and something that's unstable is in a high energy state. So this radioactive decay is a process of lowering the energy that is in this particle. Now, we have to have terms that describe a particle when it's in its high energy state, and then that same particle, once it's released some of that energy, either as a form of a particle or a wave, and before it releases the energy, or as it's undergoing that radioactive decay, we would call that a parent nuclide. So the nucleus is called the parent nuclide, and once it casts off that energy, what's left behind is what we would call the daughter nuclide. Now, nuclides that have 84 or more protons are known to be reactive. So there's a cutoff point. If you're number 83, you don't count. One thing that radioactive rays can do is ionize matter, which means that they can cause uncharged matter to become charged. And the way that these rays are doing that is they're basically causing an outer electron to be removed from an atom. Another way that it can alter, it doesn't have it here on the slide, but another way that it can alter matter is that it can create excitation. It can create a fairly low energy electron to become excited and jump into a higher energy orbital. So these are just a couple of properties that radioactive waves can act on regular matter. Now, radioactive waves, we can conclude then, have high energy themselves. They have the ability to penetrate matter and create some effects. And we have some substances on Earth that can glow. And radioactive rays, if a substance that can glow is exposed to radioactive waves, it can cause phosphorescent chemicals to emit light. Now, our understanding of this actually started with this fellow right here, Antoine Becquerel, and he designed an experiment to determine whether phosphorescent minerals gave off X-rays, because in his mind, he thought the two were connected. So let's review what phosphorescence is. This is a long-lived emission of light by atoms or molecules that occurs after these atoms or molecules have been exposed to light. So it allows them to absorb light, and then they can phosphoresce for a while after that. Now, X-rays are rays that can penetrate matter, and they can create an exposure on a photographic plate. It's telling us a little bit about some qualities of this. Now, these are both, energy waves that are being released, but they're not necessarily the same thing. But Becquerel didn't know that, and so his experiment that he designed, he thought would prove that. In fact, it didn't, but he gave us something else instead. So what Becquerel discovered was that certain minerals were always producing energy that could penetrate matter. And it didn't necessarily have anything to do with phosphorescence. So what he determined from his experiment was that all the minerals that produced these penetrating rays contained uranium, and that the rays were produced even though the mineral was not necessarily exposed to outside energy. So even though his experiment proved to failed to prove his hypothesis, he discovered something really important. As a result of what he discovered here, he called these rays uranic rays because they were emitted from minerals that contained uranium. They're similar to X-rays, but they have nothing to do with phosphorescence. So in this, his experiment failed. But like I said, he gave us an understanding of something much, much more important. Well, then along comes this little smarty pants, Marie Curie, and she determined a bit more based upon what Becquerel had just done. She determined that the uranic rays were emitted from specific elements, and she also discovered two new elements by working with these rays. She discovered radium, and it's named for its green phosphorescence and the type of rays that it emits. And she also discovered another element called polonium, which is named after her homeland of Poland. So she did some hefty work in and of herself. Um, because these rays were no longer just a property of uranium, she renamed these rays radioactivity. So Marie Curie was able to expand the work of her predecessor, Becquerel. So before we get too much further, let's review what we know about the nucleus. We know that it has a very small volume compared to the volume of the atom. Remember, it's where all the mass is, but none of the volume, and the electrons is where all the volume is, but none of the mass. We know that it constitutes essentially the entire mass of the atom. That's just what I said. We know that the nucleus is very dense. The orbitals are very not dense, but the nucleus is the dense part of our atom. It's composed of protons and neutrons that are bound together, and we could call these particles bound together as nucleons. So that's some new language that we see here in this chapter. Now, every atom of an element is going to have the same number of protons, and we call that the atomic number, and it's represented generically as Z. So we could say some atom, atomic number Z, and we're just talking about any number of any atom, just generically. Atoms of the same elements can have different number of neutrons, and we understand these to be called isotopes. Now we know that the mass of an element is made up of the protons, the mass of the protons plus the mass of the neutrons. And if we start tweaking the number of neutrons, we're going to get different masses for our isotopes. So these are the things that we know and understand about the nucleus. And what we're about to learn when it comes to radiation, because it is all about what's happening with the nucleus, is going to allow us to understanding what's on this page will allow us to understand how changes are being made to the radioactive nucleus. So before we get to talking about radiation, let's actually talk about isotopes, because there's some things we need to understand about this before we move on, and about how to write all of this. I guess that's really the big thing here. So isotopes are going to be identified by their mass number, and their mass, as we just stated, is defined by the number of protons and the number of neutrons. Now you could have an element that has that set number of protons. That's how we know we're dealing with that element. And if you had maybe two neutrons with it, that would have one particular mass. But if you had three neutrons, then it would have a different mass. So each one of those is a different isotope. It'll behave differently, and as a result, the way we identify that isotope is through that mass number, because that's the truest reflection that we can give to this isotope. So like I said, the mass number is the number of protons, which will be unchanged for a particular element, plus the differing number of neutrons. Now, the way that we would write that we're dealing with an isotope is that we take the symbol of the element, and in the subscript to the left, we would write the atomic number, the number of protons. And then in the superscript to the left, we would write the number of the mass number, the number of protons plus the number of neutrons. Now this might be given to us. So what's not here is the number of neutrons. That's not given to us. But like I said, we could calculate it. We could just take this mass number and subtract the number of protons, then we've got the number of neutrons. So the way that this abbreviation would look would be like this. So here we have the symbol of the element, the number of protons, and the mass number. Now, the nucleus of an isotope is going to be called a nuclide. We saw this language earlier when we talked about particles undergoing radioactivity. We had the parent nuclide and the daughter nuclide. So these are dynamic nuclei that are doing things. And less than 10% of the known nuclides are non-radioactive, which means that most of them are. And we would call them radionuclides, just to let the world know that we understand we're dealing with something that can cast off some energy or some particles. Now, each nuclide is going to be identified by that symbol, as we just said. And the way that we would write it is that we would have the element with a hyphen and its mass number. So this is one of the ways that we could write it. So for example, calcium 35, this is a form of calcium that has 20 protons. That's how we know we're dealing with calcium, but it has 15 neutrons. If we were dealing with calcium 36, we would have 36 here, and that we would know that we're now dealing with 16 protons. We can write it this way. This is legitimate. We can also go through the trouble to write it this way. The other way that I've seen it written is with the symbol and the mass number in the superscript and no atomic number. So there's a variety of ways that this could be written. The way that we're going to write it will either be in this form where we have the symbol with a hyphen and the mass number, or you'll actually see it written out with the protons and the mass number off to the left in superscript, subscript next to the symbol of the element. Now, radioactive decay can take a number of forms, and it's going to be categorized based upon the type of decay that it is, whether it's a particle-based decay or whether it's an energy ray. Now, Rutherford was the one who discovered the 3 types of radioactive decay associated with rays. And you might remember Rutherford as the fellow who blew a hole in J.J. Thomson's plum pudding model of the atom. So these guys weren't just hanging around, discovering one thing. They were doing a lot of stuff. So Rutherford gave us these types of rays. And the 3 types of rays are the alpha particles, the beta particles, and the gamma rays. Now, alpha particles are little particles that have a charge of +2, and they have a mass of 4 atomic mass units. And we call it a helium nucleus because what it really has is 2 protons and 2 neutrons. It gets that +2 charge from those 2 protons. And it looks very much like a helium nucleus, so that's what they call it. It's the helium nucleus. So that's what an alpha particle is. Basically, it's just the nucleus of a helium atom. Then we have beta particles. Now, beta particles are going to have what amounts to a charge of a -1, and it's going to have virtually no mass, and it's going to be more like an electron than a big old nugget that looks like the helium nucleus. And then lastly, we have these gamma rays, and this is a form of light energy, and it's not particle in nature. We associate the particles with the alpha rays and the beta rays. Gamma rays are pure energy. Now, in addition to these, we have some unstable nuclei that can emit something called positrons. And positrons are, hang on, positively charged electrons. Yeah, things are starting to get a little odd in the world of radioactive particles. Yeah, so we have a subatomic particle that is not a proton that has a positive charge to it. Some unstable So let's start off by talking about alpha decay. Alpha's got this little symbol, so you'll see that sometimes. And like we said previously, it looks like the nucleus of helium. So we have the symbol of our atom, He, helium. We have our 2 protons, and we have a mass of 4, which means we've got an additional 2 neutrons with it. And here we see our particle, some particle. This is not helium, but this thing that's emerging right here is our helium nucleus. So we have some particle undergoing alpha decay, and it's getting ready to fling off a couple of protons and a couple of neutrons. Boink, there it goes. All right, alpha decay occurs when an unstable nucleus, here's our nucleus that is unstable, is emitting this particle composed of the 2 protons and the 2 neutrons. And the way that we would write an equation for this is that we have the symbol of the parent nuclide right here. This is uranium. And we have the number of protons and its mass. So boy, we got a bunch of neutrons here with this one. And it's going to cast off a couple, and look at what happens. We've lost a couple of protons, and we have to reflect that. So we went from 92 to 90, and we're now, because we have 90 protons, we're now dealing with a new element, which is thorium. and this is our daughter nuclide, and we can see that we've lost a mass of 4, 2 protons, 2 neutrons. So our mass went from 238 to 234. And because we have to write a balanced equation, we have to explain where those went, those 2 neutrons and those 2 protons, and we have to say that it showed up here as an alpha particle that looks like a helium nucleus. Now, it's the most ionizing but the least penetrating types of radioactivity. Now, it's ionizing because these particles and these rays have the ability to knock electrons out of orbits. And it would probably make sense to us how a little particle flying around the universe would have the capacity to do that. But because it is kind of big, it's also a little bit clunky, and it doesn't have great penetration. Even though it has a little bit of mass behind it. So the way that you can protect from alpha particles is just a piece of paper or clothing. So that's reassuring. The loss of an alpha particle means that the atomic number, like I said, is going to decrease by 2, and that the mass number decreases by a total of 4, because not only are we losing 2 protons, we're losing 2 neutrons. Now, when we talk about beta decay, what's happening here is a beta particle, which is very much like an electron, gets emitted from the nucleus. And this happens because a neutron has converted itself into a proton. So our once formerly neutral particle, known as neutron, now has become a proton. And as a result of that, this little beta particle gets emitted. So the way that we would write the equation that this has occurred is that we're looking at a neutron, and it has no protons because it's a neutron. It has a mass of 1 because it is a proton, and is going to emit this particle, which is a negative proton, with no mass, because the mass is still here. The mass is still here, but our neutron has now become a proton. So that's how we would write that. We would say this little particle got emitted as a result of this charge, this gain of charge on our neutron. Now, beta decay occurs when an unstable nucleus emits this electron-like particle, and we know that one of the neutrons has now gained a positive charge as a result of that. And here's the deal about beta particles. It's about 10 times more penetrating than an alpha particle, but it only has about half the ionizing ability. So even though it can go a little further, maybe go into some other places, it's not as strong once it gets there. And the way you would protect from beta particles is through some sort of a heavy cloth. Now, when an atom loses a beta particle, what's going to happen is its atomic number, the number of protons, is going to increase by 1. That's because one of those neutrons now has a charge to it. And its mass number will remain the same because that neutron didn't go anywhere. So if we look at what we see happening here in our image, I'm going to blow up this little bit right down here. Now with beta and alpha, we saw that there is some sort of particle that gets emitted. With gamma, there's only high energy photons. So there's no loss of particles from the nucleus with this sort of radiation. So there's not going to be a change in the composition of the nucleus as a result of this. So it's going to have the same atomic number and the same mass number. And the way that we would write that there's been a gamma emission is that we would use the gamma symbol with the 2 zeros, because we're not changing the number of protons, and there are no protons associated with it, and there is no mass associated with it. Now, gamma rays are the least ionizing, but they have the most penetration, so it's going to take a little bit to be protected from them. And this is where we're going to see the usage of lead or thick cement walls, or even a couple of feet of water. So you could actually be a diver working in a nuclear reactor, and you could get as close as to about 2 feet and see what's going on. You wouldn't want to go much past that, because then you could start to get the effects of gamma rays. Gamma emission generally occurs after the nucleus undergoes some other type of decay and the remaining particles have rearranged. So this is kind of like an after effect of some other process. Positron emission is another type of decay, and what we have here is the creation of a positively charged particle that's very much like an electron. In fact, it's called the anti-electron. It has the same mass as an electron, but instead of having a negative charge, it has a positive charge. And these positrons are very similar to beta particles as far as ionizing abilities and penetrating abilities. Now, a positron is formed and ejected when the nucleus undergoes a transition where a proton turns into a neutron. Now, we've already seen a neutron go into a proton. Now we're seeing just the opposite of that. So our equation, as we see here, is that you have a proton with its one proton and its mass of 1, written out as an isotope. And what we have here is the creation of our positron, which has a positive 1 and no mass. And because we have basically moved the charge away from here, we now can say we have a neutron with a mass of 1, because neutrons do have mass of 1 and they have no charge. So that's how we would write a positron. So basically what we're doing is we're saying we had a proton with this positive charge, and now we have a neutron. And where did that charge go? Well, it got right here on this positron. Now, when an atom loses a positron from the nucleus, its mass number remains the same in mass, like I said, because positron doesn't take any mass with it, but it does take that charge with it, which means that we're going to see a decrease in the atomic number, which now means that we're talking about a new element being created. So if we look at what's happening here with phosphorus, it undergoes positron emission, and here's our positron, and we create silicon as a result of that, because we went from an atomic number of 15 down to an atomic number of 14. Let's talk a little bit about electron capture. So what's happening here is that you have an electron from an inner orbital being pulled into the nucleus. So what happens when that electron enters into the nucleus? Well, there's not going to be a particle emission, but the atom is going to change, because that electron is going to combine with one of the protons in the nucleus, and basically it's going to wipe out the charge of the proton and turn it into a neutron. So we're basically losing a proton as a result of electron capture. And when that proton becomes a neutron, we're not going to see a change in the mass number, because we're going to have the same mass, but we will see a change in the atomic number. The atomic number will decrease by 1. Now, as we've gone through each one of these examples of decay, the different decay types, we've actually seen the nuclear equations that are associated with them. And if we notice some things about the nuclear equation, the thing that you notice is that you don't have to balance the equation with the number of reactants and the number of products, because you're changing the players by moving charges and electrons around. You're changing the players that are involved, so you'll never be able to balance the number of the particles on one side, or the atoms and molecules on one side and the atoms on the other side of the transformation arrow. But the things that we do look at are atomic numbers and mass numbers, and these are the things that need to be conserved in a nuclear equation. So the sum of the atomic numbers needs to be equal on both sides of the transformation arrow, as does the sum of the mass numbers. So if we look at this example right here, we were taking uranium and it's undergoing alpha decay, and we know that because of this helium, and we start off with 92 protons. And we know a couple of those are going to leave with our helium nucleus, and then we're going to create thorium. And we know that 90 plus 2 equals 92, so we've conserved the atomic number on both sides. If we look at what we have here with the mass number, we have 238 in our mass number on the left of the transformation arrow. We know that 4 of those mass-bearing particles are going to leave with our helium proton. 2 of them are protons, 2 of them are electrons, or helium nucleus rather, and that the remainder are going to remain with thorium. So we're going to end up with 234 plus 4 equals 238. So this is what's important when it comes to balancing nuclear equations. I mean, we're never going to have a uranium on the left of the transformation arrow and a uranium on the right of the transformation arrow, because uranium has basically altered its identity and has become thorium. So when it comes to nuclear equations, it's not the elements, the atoms that we're looking at balancing. It is the atomic number and the mass number. Now this chart is really a great chart because it gives you, it tells you the type of decay that is happening. It gives you a nice visual about what's happening here, and it tells you a bit of how to write those equations. So this would be a really handy chart to keep around you when it comes to quiz and exam time. So the question is, what causes the nuclei to decompose? Well, it might help to first understand what's holding them together. So particles in the nucleus are held together by a very strong attractive force, which is found only in the nucleus, and we call this a strong force. But the deal with strong forces is that they only have action over a short distance. So, for example, if we were to have a proton and a neutron hanging out, and they weren't close enough to recognize each other, then they could just possibly just drift off and never have any sort of interaction. But if we had a proton and a neutron close enough to each other, then they could, under the influence of strong force, come together and start to make something. And even though neutrons don't have any sort of a charge to them, they play an important role in stabilizing the nucleus because they add to the strong force, but they don't have any sort of charge which could create a repelling force. So we know that protons and neutrons are being held together in the nucleus by something called strong force. Is there a way for us to predict whether that strong force is going to allow for any sort of decay? And the answer is yes, and it has to do with the ratio of the neutrons to the protons. So the ratio is an important measure of stability of the nucleus. So for example, Z represents our protons. And if you have an element that has 1 to 20 protons in it, then and the ratio between the protons and the neutrons is approximately equal to 1, then you're going to have a stable nucleus. So this is what we see if we look at the periodic chart. This is taking us all the way from hydrogen to calcium, and these are pretty stable elements. We don't see a lot of any sort of significant decay happening here, certainly no radioactive decay. But what about those elements that go between 20 and 40? Well, as long as the ratio of the neutrons and the protons comes in at about 1.25, then those two are stable. Well, what if we get to that 40 to 80 range? Well, again, as long as we have the neutron to proton ratio being about 1.5 or so, maybe even a little bit less, we're we're still looking at something that is stable, something that is not likely to decompose. But once we get to those elements that have more than 83 protons, then there is not going to be a stable nuclei present. There's no stable nuclei. These nuclei are going to be the ones that decompose. This is where we see radioactive decay occurring, is in these elements. So if the ratio, if the neutron to proton ratio is too high, then the neutrons get converted to protons via beta decay. Now, if the ratio is too low, then the protons get converted to neutrons via. Now, besides the neutron-proton ratio, the actual numbers of protons and neutrons can also affect stability. So the most stable nuclei have even numbers of protons and even number of neutrons. So everybody's equal in those scenarios. But stability is going to decrease when you have even numbers of protons but odd numbers of neutrons, or when you have odd numbers of protons and even numbers of neutrons. So when you have this mix happening between even and odd numbers, then you start to lose that stability. Now, only a few nuclei have odd numbers of protons and odd numbers of neutrons. And if the total number of the nucleons adds to something known as a magic number, then the nucleus is also considered to be more stable. So remember, the nucleons are the protons and the neutrons, and the numbers that we see here down here at the bottom is if we have the number of neutrons or protons equal to 2, then we're going to be stable. Or if those numbers are equal to 8, or if those numbers are equal to 20, or if the number of neutrons is equal to 126. So these are some magic numbers that are also predictors of stability in a nucleus. Magic numbers and stability. Now, we've seen indicators that predict the likelihood of having a nucleus that's going to undergo some decay. And if we look at some of these elements, some of them have such a large proton number and a large neutron number that we know that when they undergo decay, they're going to only decrease their instability by maybe 2 protons, maybe 1. And that means that the thing that they create by undergoing decay is also going to be unstable and undergo decay itself. So in nature, often one radioactive nuclide changes into another radioactive nuclide, so that the parent creates a daughter, and then that daughter is also radioactive, and it too will become a parent, giving off a couple of some sort of a transformation and creating a daughter nuclide of its own. Now, we understand that all protons that are greater than 83, all elements that have proton numbers more than 83 are radioactive. And all radioactive nuclides that are produced one after the other until a stable nuclide is created is known as a decay series. And that's what we see here on the slide. We see uranium undergoing a series of decay until it reaches a stable nuclide. Now, in nature, there are small amounts of radioactive minerals in the air, in the ground, and in the water, and we're exposed to them in a variety of avenues. And the radiation that you're exposed to from these natural sources is called background radiation. Typically, these are not harmful, but you know, we have moved forward, and in our advancements of utilizing different things from nature, even some things that are dangerous in our everyday life, and then we have to start thinking about protecting ourselves. And that's what we're going to see on the next slide. Now, through technology, we have been able to harness certain elements that are harmful and utilize them in ways that benefit mankind. And we see some of this in medicine. You see it in high tech. But if you're someone who has to work around this material, then you run the risk of exposure. And for your employer to understand where you stand, where you are with that exposure risk, you typically have to wear some sort of radioactivity detecting device, which is what we see here on the slide. So particles that get emitted by radioactive nuclei have a lot of energy and they can be easily detected. One of the ways to do that is through light protected photographic film. Exposure to radioactivity can cause that film to detect the presence of those radioactive rays. And what we see here is something called a film badge dosimeter, so that if you were working around doing radiographs, if you were working around radioactive substances and had to wear protective gear, you'd also want to wear one of these, and you would have that badge developed and on an ongoing basis. You'd have a new one actually, and if that film was developed or exposed, then they would know that you had reached a certain amount of exposure, and they would pull you out of rotation so that you wouldn't get repeated exposure. Or maybe there's even a problem, indicator of a problem. So yeah, you're gonna, if you choose to go into a field where you're working with radioactive substances or radioactivity, then you're going to be required to wear something like this. Now, there are other ways to detect radiation in the environment, not necessarily so much, what's happening with your specific body, but in the environment. And one of the ways that scientists were first toying with this was with the use of something called an electroscope. There were a variety of these. What we're seeing here is the one that's utilizing gold leaf under glass. So what you have here is you have this this like a bell jar, and that's going to prevent the leaves from being disturbed by air flowing around it. So you have a couple of gold leaves here. Then you insert this metal rod that makes contact with the gold leaf. And then on the outside, if you have a radioactive substance, then it will interact with the knob of the metal rod that you have inserted in here. And then the charge will travel down and it will charge the gold leaf, and it'll cause those leaves to spread apart. So this is a very early detection system for trying to figure out what was radioactive and what wasn't. But we have more modern ways um, of doing this now. And so let's take a look at one of those. Now, the Geiger counter is something that is used currently to detect ionizing radiation in the atmosphere. And the way that this one works is that it counts the electrons that are generated when argon gas atoms are ionized by that radiation that might be in the atmosphere. So if you've ever watched something like a UFO movie, or where some sort of situation in a movie where there might be radiation exposure, and you see the military types or the government people coming in, and they're wearing their heavy duty suits and they're carrying around these devices that are crackling and carrying on, those are Geiger counters. They're looking for radiation. And here's another way to detect radioactive radiation. So when radioactive rays strike certain chemicals, these chemicals will give off flashes of light. And you can have something known as a scintillation counter that can count those flashes per minute. And I looked for an image. I found this one. This is kind of standard of what I was seeing with these. This one's considered like a tabletop version, and you can see there's a readout here, and then there's this device, and then there's some sort of a processing unit here. So it's almost like a computer with a tower that lays down. And these tend to be a little bit bigger, although I did see some smaller handheld ones when I was looking around. But this was pretty much what I saw in looking for those. So yeah, yet another way. So the rate of change in the amount of radioactivity you have in a radioactive substance is going to remain constant no matter how much of it you have. And you will see a different uh, radioactive decay for each radioactive isotope. So that rate of change varies over isotopes, but it doesn't vary based upon how much of each isotope that you have. Now, the particular length of time, which is called a half-life, um, this is the time required for each radionuclide to lose half of its radioactivity. That's why it's called a half-life. Now, the shorter the half-life, the more nuclei decay every second, and therefore this is going to be a more radioactive sample, or we would say that it's a hotter sample as a result of that. So those are typically the bad boys of radioactive decay. And the rate of radioactive change is not affected by temperature. So even though we've looked at changes involving either input of heat or the elimination of heat in a change, this one happens without any temperature changes happening around it, because it's not affected by temperature. It doesn't create one, and it's not affected by them. Okay, now the rate of decay is a first order um, kinetics type equation, and we have the rate law here. The rate law tells us about the K and the N, and where the N would be the number of radioactive nuclei, and it has this sort of relationship to it. And when we go to calculate half-life, it would be the number of radioactive nuclei at a particular time given the initial amount of radioactive nuclei you started with. Now, because we know that certain radioactive substances are going to decay at a particular rate, we can use this rate of decay to let us know how long something's been around, basically. So we look at carbon dating. This is radiocarbon dating that we're going to be talking about. And we can use carbon, an isotope of carbon, to do this. And the reason why is there's several reasons why. One of which is that all things that are alive or were alive contain carbon. And that there are 3 isotopes of carbon that exist in nature, and one of them is carbon-14, and this one is radioactive, so this one will degrade. And we know that its half-life is quite a long time. It's about 5,700 years. Now, we don't see a depletion of C14 because atmospheric chemistry is producing C14 at the same rate that it is decaying. So it'll always be there because of how our world works. Now, when an organism is living, it's constantly moving and using and dealing with carbon. And so within living organisms, the ratio of C14 and C12 are constant. And it's being replenished because of the presence of CO2 in the air, and as well as within the organism. Most organisms use oxygen. There are some that don't understand that, but a lot of organisms use oxygen, create carbon dioxide. So carbon dioxide is always going to be present in organisms, living organisms on this planet. Now, once the organism dies, though, that carbon doesn't get replenished, and we start to see a change in the C14-C12 ratio. It actually starts to decrease. So by measuring the C14-C12 ratio in once living organisms or plants or any number of things, and comparing it to the C14 ratio in a living organism or plant or whatever your living thing is, we can tell how long ago that organism was alive. Now, there's a limit to using C14, and that limit is 50,000 years. So if you were to show up for carbon dating and you happen to have your 60,000-year-old shroud, it wouldn't take them long to figure out that they couldn't give you a date because it only works for about 9 half-lives of C14. So it has to be below that number in order for radiocarbon dating to work. So we know that we can use carbon to date things that were once alive. So how do we date things that were not once alive? Well, we can use something called radiometric dating. And what this measures is the amount of radioactivity in a particular radionuclide. And it doesn't get affected by environmental factors like C14 and C12 do. So by measuring and comparing the amount of a parent radioactive isotope and its stable daughter, we can determine the age of an object using half-life. So kind of, doing some backwards math with this. We can use this to look, particularly with uranium and moving into lead. And so what it would do is it would compare the amount of uranium-238 to the amount of lead-206 in volcanic rock and meteorites. And when we use those, we figure that the Earth is somewhere between 4 and 4.5 billion years old.